All right, let's dive right into our explainer on nuclear fusion. This is a pursuit that a lot of scientists and engineers actually consider to be the ultimate prize in human history. And today, we're going to unpack exactly why that is. I mean, just imagine for a second, what if a single glass of seawater could power your home for an entire year? Imagine being able to capture the exact same process that fuels the sun and the stars, and then just putting it in a box right here on Earth. That is the incredible, awe-inspiring promise of nuclear fusion. We're not talking about burning fossil fuels, and we're definitely not talking about the traditional nuclear fission plants that we use today. We are talking about literal stellar power, completely on demand. To really wrap our heads around the sheer scale of this prize, think about this number: 14 million. Fusion fuel is a staggering 14 million times more energy dense than coal. It's also roughly 4 times more energy dense than our current nuclear fission. Basically, a microscopic amount of fuel yields a monumental amount of energy.
Part 1, the ultimate energy prize.
So what's actually happening here? Well, nuclear fusion occurs when 2 or more atomic nuclei are literally forced together, completely overcoming their natural electrostatic repulsion. When they fuse into a single, larger nucleus, a tiny bit of mass is lost. But thanks to Einstein's famous equation, E equals mc squared, we know that lost mass is converted into a massive amount of clean energy. And the fuel for this? Elements like deuterium are incredibly abundant. You can easily extract them straight from seawater. The byproduct is just harmless helium. No greenhouse gas emissions, and absolutely zero long-lived radioactive waste. But if this is the ultimate clean, limitless solution, why aren't we using it to power our cities right now?
Part 2, building stars on Earth.
Well, trying to put a star in a box means we have to satisfy something called the Lawson criteria, or the fusion triple product. We need this perfectly balanced combination of temperature, confinement time, and plasma density. See, because we don't have the massive gravitational pressure of the sun here on Earth, we have to compensate with extreme heat. We are talking about temperatures exceeding 100 million degrees Celsius. That is over 6 times hotter than the sun's core. At that kind of heat, matter becomes a superheated gas called plasma. And naturally, any physical container would just instantly melt into a puddle, so that plasma has to be confined perfectly without ever touching the solid walls of the reactor. Which brings us to the ultimate scorecard for fusion, Q, or the energy gain factor. This is simply the ratio of fusion energy produced compared to the energy we have to inject just to trigger the reaction in the first place. Because creating a 100 million degree environment takes a colossal amount of power, our goal for commercial viability is to get more energy out than we put in. Basically, we need a Q greater than 1. And guys, our progress here is really accelerating, 4.13. That is the world record scientific Q achieved by the National Ignition Facility back in April 2025. They delivered energy to a fusion target and got over 4 times that amount of energy back out. It is a massive scientific milestone. It proves that net energy gain is physically possible right here on Earth.
Part 3, magnetic and laser approaches.
The heavyweight battle in the industry really comes down to magnetic confinement versus inertial confinement. On the magnetic side, we're using powerful magnetic fields to confine low-density plasma for relatively long periods, like seconds or more. Companies like tokamak Energy are building these giant magnetic donuts, specifically spherical tokamaks, like their ST40, which actually successfully hit that required 100 million degree milestone. On the other side, we have inertial confinement. This approach uses high-powered lasers to implode a high-density fuel target in just a fraction of a nanosecond. It's a really fascinating contrast: long and steady magnetic containment versus incredibly fast, intense laser implosions.
Part 4, a benchtop fusion breakthrough.
But recently, a totally unexpected rogue challenger emerged in a Nature paper. The researchers noted that electrochemical loading of a metal target at the electron-volt energy scale can actually affect nuclear reactions at the mega-electron-volt energy scale. So what does that actually mean? Well, researchers built something they call the Thunderbird reactor. It's a compact, benchtop device that uses everyday, low-energy chemistry to literally boost high-energy nuclear physics. We're not talking about a multi-billion-dollar international laser facility here. This reactor fits on a standard laboratory bench.
Their methodology completely flips the script. In Phase 1, they shoot a beam of deuterium plasma at a solid palladium metal target to kickstart a baseline of fusion reactions. But then comes Phase 2. They turn on an adjacent electrochemical cell. By electrifying the palladium lattice at the microscale, they force extra deuterium atoms into the metal. Because a solid metal lattice can naturally pack fuel incredibly densely, way denser than a magnetic or laser reactor, this simple electrochemical step forces the fuel atoms closer together. They're essentially hacking nuclear physics using basic chemistry. And the result? They measurably detected a jump in fusion-produced neutrons.
Specifically, a 15% increase in neutrons. Now, to be clear, while the Thunderbird reactor is currently only producing fractions of a watt and is still very far from commercial net energy, this 15% bump is an incontrovertible proof of concept. It proves that we can manipulate massive, high-energy nuclear reactions using simple, low-energy electrochemistry. It completely opens up a new avenue for materials scientists and chemists to jump in and help solve the fusion puzzle. Part 5. The Commercial Fusion Future. With all of these physics and engineering breakthroughs happening from the macro right down to the micro scale, fusion has officially transitioned from a cool science experiment into a massive global economic race. The momentum is just undeniable. We have over 50 countries independently researching plasma physics. We have massive international collaborations like the ITER project, where 33 nations are building the world's largest fusion machine together. And, perhaps most importantly for the speed of innovation, there are now over 50 private fusion companies worldwide, rushing toward that commercial horizon. And the private capital is absolutely exploding. Total private investment has hit $9.7 billion. Even more staggering, over $2.6 billion of that was invested in just the last 12 months alone. That is serious money flowing into these private companies, driving competition and rapidly accelerating the timeline to cross the commercial finish line. So as we wrap up, I want to leave you with this provocative thought to ponder. Will the ultimate solution to our energy crisis come from a multi-billion-dollar international laser facility, from giant magnetic donuts, or could it come from a compact reactor sitting on a laboratory benchtop? The race to capture the power of the stars is happening right now. The progress is accelerating faster than ever before, and frankly, it is anyone's game. Thanks for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.